Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our series of lectures on thermodynamics. Today we want to look at efficiency of internal combustion engines. Efficiency in internal combustion engines. If you remember correctly, if you look at our earlier lectures, we have talked about internal combustion engines. We have seen the spark ignition engine, we have also seen the compression ignition engine, and we have talked about the processes there. You know, they are four-stroke engines, and this is what we want to look at, how efficient they are. What is efficiency? Efficiency deals with performance of your system. How does it perform relative to what you expect in theory? For example, the indicated effective mean pressure. What kind of work does it do compared to what actually you get in terms of your output in practical terms? So efficiency is very, very important. The fraction. So we have the energy, the output energy, what do you get out, and what did you put in? So how do they compare? If you get 1 of 1, that means you put in, whatever you put in is what you got out. That will be 100% efficiency, and vice versa. We have seen efficiency when we have talked about the Rankine cycle, the Carnot cycle. We have looked at the efficiency of those particular systems. Now, but those, remember, those had relationship in terms of the temperature of the hot body and the cold body and so forth. In this particular case, it's a bit more different. We are talking about the efficiency of these engines. So let's call it neta. That efficiency, this neta is what I'm calling efficiency. You can call it anything, you can have a small e, there's no problem with that. But this is output energy over input energy. So what you get out when you put in, that will tell you how efficient your system is. Now, this output energy in internal combustion concept is considered as the brake power. So the output energy, consider that as the brake power, which we denote as B. That's the brake power. So that if we write now that efficiency, we can now rewrite this neta efficiency in terms of the brake power. In terms of the brake power, then the efficiency neta, we can write that as now brake power into the mass flow rate times the calorific value or Q and a constant pressure. Now, this is our efficiency. We now can call it brake thermal efficiency. Let's call it neta B. That's the brake thermal efficiency. Now, what is the fluid which you put in and expect an output from? What's the fluid which you put in the system and expect output from? That fluid is what we call the fuel. And normally is, we know what kind of fuels you add to the chamber. You know the kind of fuel which you add to the chamber. And of course, that fuel is what you want to see how much work we have gotten from that particular fuel which you have put there. So that gives us the specific fuel consumption. That is SFC, the specific fuel consumption. And this specific fuel consumption, when you're talking about this particular fuel consumption, we are talking about the amount of fuel consumed per unit brake power. Brake power. So if we use the brake thermal efficiency expression here in this system for specific fuel consumption, then what do we get? So we are saying that from the expression from the brake thermal efficiency, we can see that BP, this case, the brake power is basically the brake thermal efficiency. So we can plug in this value and see the expression we get in terms of specific fuel consumption. Now, what do we have? We now have, in that particular case, we have the brake power in terms of the brake thermal efficiency, mass flow rate, and also the calorific value of that particular fuel. So we have this as MF over brake power. And of course, we cancel like terms so that specific consumption is 1 over. Very important output here, very important result. So we are seeing that the fuel consumption in a nutshell is inversely proportional to the efficiency. Inversely proportional to the efficiency. So we are seeing that fuel consumption is inversely proportional to the engine efficiency. So that means that if you have very high consumption, then basically your engine is not, very high fuel consumption, then it means your engine is not efficient. And when you have low fuel consumption, then it most likely means that your engine is efficient. And there could be a number of things which could bring in efficiency. Faulty spark plugs, they might not be burning completely as you need to be. Faulty rings in your piston system. Maybe the oil is leaking and is mixed with the fuel and so far, so you get this burning. And if you look at your exhaust emissions, you see when you're moving around with your vehicle, it's like you are clouded in a pile of smoke and all that. Your system is not performing. Your system there could be burnt. There could be overheating in your system as a sort of damaged cylinder head gasket. So many things could be happening to your system which can bring in all this manner of inefficiencies. In terms of fuel, you could have blocked fuel system in terms of filtration of your fuel. Maybe the fuel filters are blocked, so not enough fuel is going. Maybe even in terms of adjustment of the ratio of air to fuel, there is not properly tuned. So there's problems, so many problems. The tappet clearance in terms of the valve clearance and so forth. All those can lead to those inefficiencies. So when we talk of efficiency of the system, it's not like one thing. It is a myriad of things. It's a cumulative action of inefficient processes within that system. Now, what are we looking at? So we have seen that for fuel consumption is inversely proportional to efficiency. Inversely proportional to efficiency. In other words, for efficient systems, if you have efficient system, your fuel consumption should be reasonably low. If you have high consumption, then probably, again, your system is inefficient. So that's very, very important for us to note. So this efficiency is not just in terms of, there's the thermal and mechanical component. So when you're talking of efficiency, there's the thermal and mechanical components. Thermal and mechanical components, they're both contributory. So that if you look in terms of, for example, when you look at your pressure volume diagram, which you're now very familiar with, because that's an indicator diagram, very tells us about work in the system. So if you look at your indicator diagram, pressure volume diagram, so here we have cylinder volume, cylinder pressure. So we have our system. It's just a sketch, but you're now familiar with them. A sketch here. We have this knob here. This knob is associated with pumping loss. And this pumping loss, which you have there, that pumping loss is a sort of viscous friction, which is normally occurring mostly in the intake stroke and in the exhaust stroke. This is associated with viscous friction, which occurs in the intake stroke and in the exhaust stroke. So that's why you find, for example, that when you have the indicative mean effective pressure, that is that pressure which results in the expected work, what you expect in an ideal situation, in terms of the expected, let's call it expected torque output, you find that it is not exactly what you get. So that if we go back to our expression, for fuel consumption, we find that the efficiency here, where we talk of the indicative power or work resulting from our systems there, which we are used to, then we have this component. So these two components, this overall efficiency, we have this component that is the mechanical component and the indicative component. Let's call it indicative component. Indicative power. Let's call it in its normal form. And so the difference between these two quantities, because when you look at what you expect as power output in an ideal situation and what you get, there is a difference. And these two differences here, because the indicated power and the mechanical is basically associated. There's a power loss associated with those friction elements. There's a power loss associated with those frictional elements. Now, we have talked a lot about brake power. Brake power. We've talked about brake power. And it is important to know what this brake power is. Brake power is very simple. It's simply the torque. Times the angular speed, omega. That angular speed is not an omega. And this omega, that's the angular speed, can be gotten as, or you can have it as theta per T. And what's that theta? That theta is 2 pi n. What is n? That's the revolutions per minute. This RPM. And even think is a machine cycles per unit time. And so, this angular speed, therefore, is 2 pi n over 60. So that the brake power is the torque, and the crankshaft. Remember, torque is just force times displacement times that's the brake power. That's the brake power. So very, very important. And remember, torque is responsible for the rotational force. So that's how we have transmission in our systems. So that rotation is passed through the transmission system, and of course, finally, you have your vehicle moving. You have your vehicle moving. Now, in terms of efficiency, if you consider a series of fuels, that is, the question you're asking yourself, how will efficiency vary depending on fuels? Especially when you're dealing with fuels like biodiesel. If you take, for example, tobacco seed oil methyl esters, you can have different fractions and test the mechanical efficiency. So if you have the mechanical efficiency, and you have the brake power, you will find that there's not much difference. There's not much difference between the various combinations. There's not much difference. There's not much difference. No major difference. For example, if you take a biodiesel, like the one from tobacco, seed, tobacco seed oil, methyl esters, the TSOM. You will find that despite the different ratios, there's a much difference, because basically, technically, there's no big difference in terms of calorific value of these fuels, what we can call the fuel power. When you can call the fuel power, which is simply comes that. And the internal energies of these fuels, if we go back to our earlier lectures on bomb calorimetry, you're going to see how we are able to determine this particular quantity. I encourage you to go back and see some of these lectures. It assists so that you build on what you know. That's just the caloric heat capacity, which is simply the change in internal energy with temperature and a constant volume. Simply change internal energy and a constant volume. Or you can think of du as being CV dt. This is infinitesimal terms, or delta U is equal to CV delta T. So that particular quantity there gives you basically the energy content of your fuel, and it's a very important unit. So the fuel power, just multiply mass flow rate with what you have in terms of the heat capacities. So in a nutshell, you cannot achieve 100% efficiency. So at full load, your system will probably be operating between 80 to 90% efficiency. I get 100% efficiency. And like we have said, the cause for these disparities in these performances, inefficient performances, are numerous. So one needs to tidy up the machine system systematically so that you come up with really what is the issue, what is exactly the issue causing those losses. But ideally, the efficiency should be improved to higher levels so that you have lean fuel consumption, and that makes you more productive than the wastages resulting from this inefficiencies, factors resulting in those inefficiencies. So I think we'll stop at that point.